So let's begin with a quick recap on product types. As with any other construction in homotopy type theory, we can informally interpret product types in three ways. So far, we've mainly focused on the homotopy interpretation, where we're taking the product of spaces. So I can multiply one space times another. For example, I can multiply a circle times a circle, and I get the torus. In this video, we're going to talk about the programming interpretation of how we can actually work with product types in a programming language. And for the logic interpretation, I want to say a little bit more about this, so we'll save it for a future video. But if you are a logician, then these rules right here should tell you everything you need to know to figure out what the logic interpretation of product types is. Speaking of rules, those rules were part of our formalization of product types in the HoTT deductive calculus. So this rule right here is the introduction rule, allowing us to introduce terms of product types. Last time we also saw the beta and eta rules for product types, which tell us what happens when we introduce and then iterate, or iterate and then introduce. And so the final piece of the puzzle is to incorporate this into our Agda formalization. So let's get to it. So let's jump into Agda. In order to introduce product types into our Agda formalization, we're going to make use of a new syntax, which we haven't seen so far, which are record types. So here's how we declare a record type. We say record, and then we give the name of what we're declaring. In this case, we're declaring a infix operator times. And then we give its arguments, so that this is going to take in two types. And it's going to produce a type. So if A and B are types, then A times B is going to be a type. That's what this says. Then the where keyword. And what we do is we say field, and then we list the different pieces of data that we have to include in our introduction rule. So here I'm going to say first is an A, and second is a B. And so what this says is that if I have a term of type A times B, then I can say first of that term to get a term of type A, and I can say second of that term to get a term of type B. So let's look at an example. And so let's use our example that we've been running with of ranks and suits of cards. So if I'm trying to define a function which takes a rank times a suit and produces a color 3, like we covered in the previous video. So rank times suit to color 3. And I have some argument z. When we create a goal on the right-hand side here. So here in this example, I have a goal which needs to produce something of type color 3. And if I look at my context, I have z here, which is rank times suit. And so if I split into cases on what z is, so I do cases on z, we'll see that an argument of type rank times suit, and this is kind of bad syntax, we'll make it better in a moment. The term z of type rank times suit consists of a first and a second. I'm going to rename these to be R and S. Often whenever you do casing on some variable, Agda will give names that aren't very good. And so now I see in the context of my goal that S is a suit and R is a rank. So like I said, this notation isn't very good. So what we can do is, going back to our declaration, we can add a constructor. And so we say constructor. And remember, our constructor for product types was a comma, was pairing. So I'm going to put a comma and reload. So now if I case on Z, now it says that every term of type rank times suit is constructed using the constructor comma. So it's some, I'm again going to rename this R, and I'm going to rename this S. And so now we see that every term of type rank times suit is a pair of a rank and a suit introduced using this comma. And so now what I'm going to do is I'm going to case on the rank and the suit to define the same example that we had from the previous video. Okay, that was a lot of casing. But now what we've done is we've defined this function from rank times suit to color 3 just by breaking into all the individual cases, all 52 of them. Now what I want to do is define some function combinators for product types. So what a function combinator is it's a thing that combines functions to get other functions. The first combinator that I'm going to define is one that's really important in category theory for talking about products. I'm going to denote it with this triple ampersand. And what ampersand does is, well, for any A, B, and Z, which are types, here's what it does. If I have a function Z to A, and I have a function Z to B, then I can combine these to get a function from Z to A times B. So intuitively what this is doing is if I give this a function f and g, it's going to take an argument from Z, and it's going to apply f to it to get an A, and it's going to apply g to it to get a B, and then I pair those together to get an A times B. So if I say f and g, so this is an infix function, so these underscores are the first two arguments, this function from Z to A and this function from Z to B. So that's, I'm going to call those f and g. And then it returns me a function, and so I'm also going to take in an argument for that function, which I'll call z. And so we'll see that when I load this, my context says that I have an f from Z to A, a g from Z to B, a z in Z, and I need to produce something of type A times B. So this is an opportunity to introduce a new command, which is the refine command, Control-C, Control-R. And so we see that this inserts a comma and then two more goals. So what refine does is it looks what goal I'm trying to solve, in this case A times B, and it looks at the kind of canonical way to construct something of A times B. And so the canonical way, the way to construct something of type A times B, is using the constructor of product types. And so it goes ahead and inserts that for me. So now I have a goal, a comma, and a goal. And you see that my goal 0 is something of type A, and my goal 1 is something of type B. And so now to get an A, I just apply f to Z, and it accepts that. And then to get a B, I apply g to Z. And so now we have our combinator and. So just a quick example of what this looks like. If let's say I have some function f, and I'm going to have f go from booleans to rank. And so I'll just say fb is a goal. And so these, I'm just cooking up a particular example here. It doesn't really matter too much. So I'm going to case on B. And remember, our two booleans were called on and off. Often they're called true and false in some other languages. And so now I need to come up with a rank for each of these. So I'm just going to say king and queen, because why not? And then I want to have another function, g, which also goes from Booleans. And this time I'm going to have it go into suits. So I'll have g of b and set up a goal. And then I'm going to case on that b. And so in this case, I need to produce two suits. So for one of these, I'm going to give diamond. And for one of these, I'll do clubs. So now I have two functions, and I can use and to pair them together. So if I infer the type of f and g, then it tells me it's from 2 to rank times suit. So look at the types. So 2 to the rank, 2 to suit, I can combine them to get a function of 2 to rank times suit. And I can compute with it as well. So if I say f and g applied to the Boolean on, I get king of diamonds. And if I apply f and g to off, then I get the queen of clubs. So you can trace through why those compute that way. Let's do another one. This one I'm going to indicate with star, star, star. And this is also going to be a thing that takes two functions and produces functions on product types, but it'll be a little bit different. So this one is also going to work over some arbitrary types, A, B, and Z, but now I'm going to add one more. I'm going to add Y. And so here's what this one's going to do. It's also going to, like I said, it's also going to take in two functions. So the first one will go Z to A. But now instead of going from the same domain Z, the second one's going to go Y to B. And it's going to put these two functions together to get a function of type Z times Y to A times B. So here, let me look at our goal in context. So we have an x here of type z times y, and then we have these two functions, and we want to produce something of type a times b. So we can use some of our Agda commands. So first of all, we can split on this variable x, because we know it's of type z times y. So we can split that into a pair, and I'm going to rename these as z and y, just to remind us. And so now our goal is to prove a times b. And again, we're going to use refine on that, because if we're trying to construct something of type a times b, then that's going to be a pair. And so first we need an a. And this a, well, we have a function f, which takes z and gives us an a. And we have a z. And so we can just say f of z. And similarly here, we're trying to get a b, and we have a function g, which takes a y and gives us a b, and we have a y, so we can just say g of y. And that defines our star, star, star combinator. So going back to this example with f and g, so remember if I did f and g, the type of that was bool to rank times suit. Whereas now, if I do f star 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 g, that's bool times bool to rank times suit. So it takes in two booleans, it applies f to one and g to the other, and gives us a rank times a suit. So for example, if we did f star 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 g, and we give it, say, on and off, then that'll give us the king of clubs. So you can try out the 4 different possibilities of all the different terms of type bool times bool and see all the different kind of combinations you get. So this was kind of a contrived example, but let's go through a more extended example which shows how you can actually use product types, and in particular this combinator. So in mathematics, remember that when you divide one integer by another, you don't always necessarily end up with an integer. For example, if you do 5 divided by 2, then you get 2.5, which is not an integer. But in computer science, we often care about integer division, which doesn't just result in one number, but two, the quotient and the remainder. So for example, if I did 5 divided by 2, then I could say that that's equal to 2 with remainder 1. Or if I did 15 divided by 4, that would be 3 with remainder 3. So here's the key properties, that if I do n integer division by d, then if I get back two numbers, q and r, the quotient and the remainder, then two properties should hold. First of all, q times d plus r should be equal to n. And secondly, I want that r is at most d. And so this is the integer division problem. Given n and d, I want to find q and r satisfying these two properties. And so we're going to do this recursively. So to see how this recursive algorithm is going to work, here's several numbers, integer divided by 7. Now you can probably see the pattern here, is that if I jump down from 87 to 80, or 80 to 73, then the remainder is the same. And the quotient, the first number, just gets incremented as I go up. And if we go all the way to the bottom, then this kind of ends at 0, 3. And so this gives us a recursive strategy to calculate n integer divided by 7 for any n. I just jump down by 7 until I get low enough that I can just return 0 and the remainder, in this case 3. Here's that expressed a little bit more precisely. We have a base case of if n is less than d, then I just return 0n. And otherwise, I take d away from n and do that integer division to get some q and r, and then I increment the quotient. So let's implement this in Agda. So notice from our algorithm that we have to check whether n is less than d or not, and then do two different things. So remember from a few videos back, we have a less than operation, which takes two natural numbers and gives us back a Boolean. So for example, I could say, is 7 less than 3? And it would give me off, which is our version of false or no. So we're going to use that in this example. So we want this integer division operation to take a... So we want this to take two numbers, our n and our d, and then return a pair of q and r. So we'll say n integer divide by d, and now we have to produce a pair of q and r. So like I said, we need to check whether n is less than d, and so we're going to use our Boolean valued less than, and do one thing if it is less than, and do another thing if not. And so let me set up an if then else. So if then else. So here we need to put a Boolean, and so we're going to say n less than d. And let me format this a little bit nicer. Okay, so in this base case, looking back at our algorithm, we know that if n is less than d, then we're done. We don't need to do any recursion. We can just return 0n. So I can set that up. So I want to return 0 as the quotient, and I want to return n as the remainder. The else case is the more complicated case, because now we know that n is at least d. We need to pull off d from n and get that quotient, and then add one more to it and return the same remainder. So here's our context. We just have d and n, and we need to figure out what is the integer division of n by d in this case. So we can do n minus d. So that is imported here from the Agda built-in natural numbers. If we were really doing this, we'd have to define what n minus d is, but we're just taking that as granted. So we can do n minus d, and that's a natural number. And we can even do n minus d, and then do integer division by d. So we can do our kind of recursive call. So that makes sense in the context of this goal. And that'll give us back an n times an n. And so if we do n minus d divided by d, then that'll give us back two numbers, and we need to increment the first one. And so there's a number of ways of going about this, but to start, this will allow me to introduce another construct in Agda, namely where clauses. So where clause allows me to use some term and then give a definition about it. So here what I'm going to do is, for the context of this goal, I'm going to have a increment first operation, which takes a pair of natural numbers and gives me a pair of natural numbers. So I'll say z for now. So let's replace this z with, we know it's going to be qr. So, and then we're just going to return, let me load that. And we're just going to say q plus 1 r. Oops, got to put a space. So now I have this inc first operation. So it'll take a pair of natural numbers and increment the first one. And so in this context, it'll make sense to say inc first of, in this case, what I want to do is n minus d integer division by d. So that will make sense, and that'll give us something of the right type. And so that's exactly the expression I want, is inc first of n minus d integer divide by d. Okay, so we get this kind of weird error. It says termination checking failed for the following functions, and there's problematic calls. So this gets into something fundamental about what Agda is for and what Agda is doing. So here I've implemented basically the same function in Haskell. So notice there's only minor differences in notation. So I have to write int here instead of natural numbers, and this is the notation for int times int. So you just write them as a pair. That's how Haskell denotes these things. But otherwise, it's the exact same function that we just wrote. We do inc first of n minus d divided by d, where inc first takes a pair and increments the first. So if I run this, Haskell doesn't complain about it at all. Cool function, works great. And so I can say 15 integer division by 4, and I get 3 remainder 3. I can say 87 integer division by 7, I get 12 remainder 3. So this works out great in Haskell, and there's no problem. So why is Agda complaining about it? Why doesn't Agda like this? Well, it turns out I can tell Agda to not worry about it. Just trust me. So if I put this little pragma on top of the function saying terminating, that shuts Agda up. Everything's fine. And so now I can say, oh, what's 87 integer division by 7? And it works out fine. But actually, Agda was a fool to trust me, because look what I can do. I can say, what's 15 integer division by 0? Okay, so maybe we shouldn't do that. So what happened here was I was lying to Agda. This isn't terminating. And so the problem is that if I put in 0 as d here, then this n minus d will just give me back the same thing as n. And so in order to calculate n integer division by d, I need to do n integer division by d. And so I'll find myself in an infinite loop. And so this is what Agda was trying to warn me about. A language like Haskell is perfectly fine allowing you to write code that potentially might loop forever. It's your job to make sure it doesn't. Whereas Agda, we're more worried about that, because if I'm allowed to write code which potentially infinite loops, that it turns out that would allow me to prove things that are actually false. And so Agda has a built-in checker to try to make sure that anything I write is actually going to terminate. And so it doesn't like this. Now there's ways I could be more honest to Agda and not implement a piece of code that doesn't terminate. So I can implement a version of this integer division algorithm which is in fact terminating, so I don't actually have to lie to Agda. Let me do that really fast. I won't go over it, but I encourage you to read through it more carefully and see exactly what's happening. Okay, so this version works out, and it does the same thing as the other version. So if n is less than d, then it returns 0n, and otherwise it does n minus d divided by d, and then increments the first thing. And so it will still work out. If I do 87 integer division prime of 7, it'll still give me 12.3. But the difference here is I have this other argument, which is called a fuel argument, which Agda can see is always going to be strictly decreasing, and so I can't ever find myself in an infinite loop. If I do give it 0, then it will actually exit out of the loop. So we can see here that if I do 15 integer divide prime by 0, then it doesn't crash. It just returns back 1515, which if you compare to the two requirements we had earlier, it only breaks the second one in a very minimal way, and it still preserves the first one. So even if we try to divide by 0, it still stays pretty okay. But yeah, this is a slightly more elaborate trick, and there are more principled ways to do what I'm trying to do here. But this is a kind of a simple workaround to not have to lie to Agda and potentially open ourselves up to infinite loops. So let me conclude by noting one thing, is that inc first here is of the form product arrow product. And remember what our star 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 combinator did was it produced a function just like that, of one product to another. And so actually we can, in this example, we can eliminate out the need for this where clause by implementing inc first inline using the star 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 combinator. So remember the star 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 combinator, what it did is it took a pair of arguments and it applies the one function to the first argument and the other function to the second argument to get another pair. And so here we need to star together two arguments, and notice that what we're doing in the first argument is we're just adding 1. And so that's actually just the successor function. Whereas in the second argument, we're not doing anything. So we take in an r and we just return that r. And so that's actually just the identity function. And so we could write inc first as suck *** id. And so that actually allows us to completely eliminate this where clause. And now we have the function implemented just in line like that. So I think it's a matter of taste whether this is actually an improvement to the function. I think the previous way of writing it makes it a little bit more obvious what's going on. And so maybe as a piece of software, maybe the prior way of implementing this was a little bit more clear. Whereas this version is a little bit more concise and a little bit more slick. And if I were trying to prove the correctness of this, then maybe it would be easier because I probably already would have proved some properties about how *** works. And so I wouldn't have to go through proving how inc first works. I could just use existing proofs about how *** works. So a bit of a trade-off, but your tastes may vary about which one's better. So that's all for now. We've covered all of our bases on product types, except for the logic interpretation, which, like I said, will come in the future. So thanks for listening.